Right, so the next paper in this session is Uniform Low-Cost Multipath Routing for Reconfigurable DC Networks. And Jialong Li. He's a postdoc at MPI Informatics and with a PhD.
No, that's not me.
That's not you?
I'm Cong Liang, negotiator.
You're a negotiator?
Yeah. The second one.
Okay, sorry. I misled everybody. The paper we're going to have now is NegotiaToR towards a simple yet effective on-demand reconfigurable data center network. And we have Song Liang presenting for us.
Okay, thank you. Hello, everyone. I'm Cong Liang from Tsinghua University. And today, I'm going to talk about our work, NegotiaToR. With more and more applications running in the cloud, traffic demands in data center networks are increasing rapidly. And traditional electrical packet switching faces capacity limitation in the post-Moore's law era. And optical switching, with its high capacity and low cost, has drawn researchers' interests. Unlike packet switching, in optical switching, the topology needs to be reconfigured first before the sources need to send to a different set of destinations. And recently, AWGR-based technology has reduced this end-to-end reconfiguration delay to within 10 nanoseconds, which is sufficient for faster reaction to dynamic traffic patterns among TORs. And it can also expand to DCN scale. For example, if we have high power count AWGRs, we can use a huge AWGR switch to connect all TORs together. And however, for low port count AWGRs, which are more accessible, we can connect them using the thin cloth topology. And this is a practical alternative. For both topologies, the sources tune their wavelengths and send data synchronously. And the data is forwarded to different destinations according to their wavelengths. And with fast reconfiguration and DCN scalability, we think AWGR-based technology is ready for data center networks. And the next question is how to schedule these fast reconfigurable optical links. Here we are actually talking about getting non-conflicting paths from sources to destinations because optical links are bufferless and the conflicts will lead to data damages. We also want this scheduling to be rapid to enable fast reaction to the dynamic traffic patterns in data center networks, especially among TORs. One solution is traffic oblivious. It reconfigures the network according to predefined round-robin rules. This is practical. It's a schedulerless design is practical, and which is very important when it comes to industrial deployments. However, due to the mismatch of the topology and traffic demand, it can suffer from sacrificed latency and goodput. Another solution is on-demand, which adapts the topology according to real-time traffic demands. And this can potentially provide better performance. However, there exists practicality concerns, mainly because the fast on-demand scheduling requirement. A centralized scheduler can do the job, but will introduce excessive complexity. So we ask this question: is there a practical yet high-performance on-demand distributed scheduling architecture for reconfigurable data center networks? This is challenging. Firstly, scheduling itself often leads to more complexity. Measurement of traffic demands, especially flow-level traffic demands and sources, and calculation like ordering by size, all adds complexity, especially under the context of fast optical switching. And then to support a distributed algorithm, the TORs should frequently exchange scheduling messages with each other. A separate control network will do the job, but at a significant cost. Finally, ensuring low latency for mass flows, especially under incast, is not easy work to do, because as long as the scheduling delay exists, mass flows cannot be sent timely, leading to downgraded latency. And considering deployment practicality and following the principle of Occam's razor, we present NegotiaToR. an on-demand reconfigurable DCN architecture towards a simple yet effective design. Regarding these challenges, we present negotiator matching algorithm, which is tailored towards minimalist on-demand scheduling on flat topologies. And we use two-phase epochs to support in-band pipeline scheduling and one-hop data transmission. We also provide a mechanism to bypass the scheduling delay for FCT optimization. Next, let's go into the algorithm first. There are two kinds of conflicts when scheduling the optical links among TORs on flat topologies, one-to-many and many-to-one. This is actually a matching problem. Similar problems have been seen decades ago in crossbar packet switches. And one crossbar packet switch needs to get non-conflicting input-output matches to forward data packets or data cells. Many works have been done in this area which have been proven fast and practical, along with extensive implementation experience. And inspired by one of these works, RRM, we present negotiator matching, a matching algorithm focusing on TOR level matching on flat topologies. Let's see an example on the parallel network topology first. In this topology, each port can receive from all TORs, and we should choose one of them from all possible sources. And each TOR has multiple ports, and we need to schedule them simultaneously. Now, let's assume TOR1 has traffic to send to TOR2, and TOR3 has traffic to send to TOR2 and 4. The first step of negotiator matching is TOR level request. Here, the sources check their local queues and send binary requests to destinations with no data size or priority information. And now, the destinations are aware of multiple TORs requests, and they need to resolve destination-side conflict. To this end, following RRM, we use a grant ring. The pointer of this grant ring indicates the highest priority source from all sources, and with the priority diminishing in a clockwise direction. And after granting one source, the pointer is updated to the next source in the round-robin schedule, effectively ensuring fairness while avoiding a starvation in port allocation. And to further improve fairness, all ports in TOR2 share the same grant ring, and TOR2 thus can utilize this ring and allocate these requests to all of its ports in turn. As for TOR4, there is only one request, so it just allocates this request to all ports. And then the destination sends the grants back to the sources, and the sources are aware of grants from multiple destinations, and they use per port acceptor rings to choose one grant for each port. And this marks the finish of one negotiator matching scheduling process. The tunable lasers at sources then tune their wavelengths according to locally derived scheduling results with no need for the result delivery. Negotiator matching can also be adapted to other flat topologies. For example, the thin cloth topology we said before. Here, unlike before, a port can only receive from a subset of TORs, so we need to modify the rings to match the topology's capability. For example, here, because the first part of TOR3 can only receive from TOR1 and 2, so we give it a per port grant ring with only TOR1 and 2 in it. Negotiator matching thus is adapted to the thin cloth topology. And now we have the scheduling algorithm. To enable its running, we need to provide full match connectivity among all TORs because they need to exchange scheduling messages with each other. And following previous practices, we use round-robin reconfiguration to work as full match to do this. And the intuitive solution looks like this. Firstly, the network reconfigures itself according to round-robin rules, and the sources thus can send requests to destinations. However, the destinations cannot receive the request immediately because there exists one-way delay between TORs, which is typically like microseconds. And such delay also exists between grants and accepts. During the delay, sources can only wait, leading to link waste and leading to a downgraded output. To address this, instead of running only one scheduling process at the same time, we run 3 of them simultaneously. This way, after each round robin, a set of accepts can be given, and the data transmission can be done immediately after these accepts. And this forms negotiator epoch. TORs in negotiator run synchronously in fixed time intervals called epochs. Each epoch is composed of 2 phases, the predefined phase and the scheduled phase. In the predefined phase, reconfigurations happen frequently, and providing predefined connections supporting pipeline distributed scheduling. And in one scheduled phase, the connections are fixed, providing on-demand connections supporting data transmission through one-hop direct paths. And now, with pipeline scheduling, links can be better utilized for higher output, but as for latency, mass flows can still suffer from long scheduling delay. Let's look at an example. Suppose there is a source-destination TOR pair that has no traffic to send before, and after new traffic arrives, it requires at least 2 epochs before the request can be accepted. This is even the lucky case. The scheduling delay will be long when conflicts happens. And this will lead to long mass flow FCT, especially under incas, adversely affecting application performance. If we can bypass the scheduling delay, FCT can be optimized, and this leads to our scheduling delay bypassing mechanism. Recall that in the predefined phase, we provide full match connectivity, supporting exchanges of scheduling messages. This is actually a perfect opportunity if we have urgent data to send. So in this opportunity, we utilize it and also piggyback small data packets along with the scheduling messages. This guaranteed unscheduled transmission are sufficient for mass flows, which are small in size. And one problem is, what if mass flows are header line blocked by elephant flows? And we can use, to maximize these opportunities, we can use a prioritization of mass flows as sources, like PS. Now, the main parts of negotiator have been presented. We like to emphasize the design efforts towards practicality. Negotiator matching is inspired by, like RM. We can borrow the proven implementation strategies from them. For example, using the programmable priority encoders to implement rings. Also, its other designs like no iteration, no data relay, binary request, and stateless scheduling all contribute to its reduced complexity. They are simple, and that's good. But one question is, could a more complex design significantly improve negotiators' performance? For example, what if we add iterative scheduling to it? And this is also the practices in crossbar switch port matching. We show that this is not a good fit because a negotiator has a longer delay between consecutive steps. When there is no iteration, it requires like 2 epochs for the request to be scheduled. But when there are 3 iterations, this becomes 6. During long scheduling delay, data may already be sent. Data corresponding to the request may already be sent, leading to outdated requests. And this will lead to possibly downgraded performance. And this has been confirmed by our experimental results. We have also done other similar explorations. Please refer to our paper for more details. Here, we will briefly introduce our main evaluation results. We set the simulation to contain 128 TORs. They are connected by 2 representative flat topologies. And for practicality, results without mass flow prioritization is also shown. Results show that negotiator achieves both small mass flow FCT and high output on 2 representative flat topologies. Particularly, mass flow FCT is orders of magnitude better than the traffic behavior scheme. And to sum up, we present negotiator, an on-demand reconfigurable data center network architecture towards a simple yet effective design. We present negotiator matching algorithm which is tailored towards minimalist on-demand scheduling on flat topologies. We use two-phase epochs to support in-band pipeline scheduling and one-hop direct transmission. We also provide scheduling delay bypassing mechanism for ICT optimization. By leveraging the fast reconfigurable optical hardware, this kind of technology to support high performance with low complexity, we hope that NegotiaToR can facilitate the development of next generation reconfigurable DCNs. Thank you.
Thank you. Wow. I think something unheard of in the history of SIGCOMM, a talk ending 2 minutes early. All right.
Okay, hi, very nice work. Yiting Xia from Max Planck Institute for Informatics. So I'm wondering if your negotiation protocol will run into consistency issues because it supports multiple requests at the same time. And it seems you also have a default schedule and augmented with real-time scheduling. So could you comment on the consistency issue?
By consistent issue, you mean like time synchronization or?
No, I mean, for example, what if you come up with several schedules that conflict with each other? Or in the worst case, can they run into deadlocks?
Normally, this kind of thing won't happen. And because one design of NegotiaToR is that it's stateless. It's just a process all the messages is received and send the results back. It doesn't care about states.
Okay, maybe I missed that. Thank you.
Yeah, thank you.
Thank you. Nice work. I have one simple question, like if a TOR sends multiple requests, is it possible that this TOR receives 0 grant? Is it possible that?
It is possible. Yeah, it is possible. If in unlucky cases, all requests are rejected by destinations, it's possible. Yeah.
I have a very simple, dumb question. Like how large a data center network can you build as a flat topology? So what is the typical radix of like this?
Because this design is our flat topology is built above TORs, so this can support more hosts, I think.
Don't you want to aim for like 2 TORs to be connected to each other? Otherwise, with failures, you'll have a lot of indirection.
Yeah, indirection, you mean?
Okay, we'll take it offline.
Okay,
All right.
thank you.
Okay. Thank you. Thank the speaker.